No, go back. So we ended Wednesday looking at this aldol reaction. We might get to some more aldol stuff by the end of the day. I would be kind of surprised, but maybe we do. It's not going to change the exam. The exam's already written. There's one question total on the aldol concept. I group aldols as a massive subject. So pretty much, if it involves carbon in chapter 18 as a nucleophile, that's aldol. Okay, so chapter 18 is oxygen and nitrogen. That's where your focus is. And I just remembered I wanted to add more questions into the exam on that. Oh well. So no carbon nucleophiles from chapter 18, which is really looking at enolates. Okay? So enolates are on the exam. They're carryover from chapter 10, so you are responsible for those. We're responsible for enolates explaining acid-base characteristics and other fun stuff like that. But we aren't looking at enolates as nucleophiles with other carbonyls. So in a nucleophilic addition reaction, which is what our aldols are. There's a bunch of name reactions that go along with it. We'll be looking at those named reactions, and I will complain prolifically about each and every single one of them because they're all the same basic chemistry and there's nothing new or exciting about them. And admittedly, I have not looked them up enough to see how ancient those names are, but my impression is those named reactions all happened relatively recently, and for that reason, they don't deserve to be named reactions, in my opinion. Okay, so I'll complain about them then. But yeah, so there's the basics of our aldol. Almost always followed with a condensation. We almost always do that last elimination. We'll talk about that real quickly. Why can I do that elimination? So what is happening in that last step? You're right, we are losing a hydrogen. Okay. We'll go ahead and color code it as a red hydrogen. The base is coming in, removing that hydrogen, forming the pi bond, and kicking out OH as a leaving group. Okay, so a couple things look a bit odd on that. Number one, we have hydroxide as a leaving group, okay, which everybody tends to freak out and say, oh my god, I can't do a hydroxide as a leaving group because hydroxide's a bad leaving group. It's leaving into a solution that is effectively full of hydroxide. Okay, so it isn't as bad of a leaving group. It's not like it's leaving into a system that is weaker than it. It's leaving into the same environment. The next question would be about the hydrogen. Okay, is that red hydrogen acidic? Yes, it is acidic because resonance stabilization as enolate chemistry with the carbonyl. Okay, so we're responsible for that. Okay, the next part about it is that red hydrogen is roughly the same as the blue hydrogen that we lost at the very beginning of this whole reaction. Okay. That hydrogen that we removed to initiate this whole cascade, okay, was also acidic because resonance stabilization with the enolate. Well, which one's more acidic, the blue one or the red one? The red one is actually more acidic because there's an inductive withdrawing effect from that oxygen that we've attached to that structure. Okay? That inductive effect makes the red hydrogen more active than it started. So if we got it started, the reaction's going to continue to deprotonate. Okay? So we could just make the argument, well, it just deprotonates and it does the enolate stabilization and that's it. Okay? It does actually do the full-on elimination and ejects the hydroxide because we take a look at our product. What is special about this product? It isn't so much that it's a basic environment. It's that those two pi systems are conjugated. We've stabilized the pi system. Conjugation now increases the stability of that product because it is more stable, it is now lower in energy, and it provides that extra driving force to actually finalize this reaction. Okay? So when we're thinking about our aldol reactions, almost always they'll go through and do the second condensation, or the last part of it, that condensation or elimination step. Okay? If you didn't want the condensation or elimination, typically you're told, don't do it. Just do the aldol part. Okay? All the different named reactions come about because of our starting structure. Well, if that's an aldehyde, then we get one product. If it's a ketone, we get a different product. The chemistry is still the same. Okay? If it's an ester, we get a different product. Okay? If it's now reacting instead of with, say, another carbonyl, like in this case the aldehyde, but instead reacts with, say, this structure, whoops, which of course I had to draw wrong. This structure, what changed? Okay, well, this carbon, our nucleophilic carbon, is a weak nucleophile. Yes, that's and sorry, weak is a bad word for that. It is a strong nucleophile, but it is not stupid strong, which means when I react it with the red structure, where does it attack? It's going to attack the positive position, which is where? The carbonyl? No, it actually attacks the beta position.
It's a 1,2 direct addition, right?
Not the enolate. The enolate is actually a 1,4.
Always?
Yep.
But that's only aldol, right?
In the aldol, it's going 1,2. A very strong argument can be made that we shouldn't be calling it 1,2. Why in the aldol should we not call it a 1,2? What are the addition products? Where can that nucleophile attack? This is the structure I'm reacting it with. Where can my nucleophile attack?
Carbonyl.
Carbonyl carbon. Where else? That's it. That's literally it. Can't attack anywhere else. Okay? So while that is technically a 1,2 addition, we would never reference it as a 1,2 addition because we aren't adding information to it. Okay? There's only one reaction site in that case. Only when you drop in that next pi bond that we now split and differentiate 1,2 and 1,4 because now it's important. There's two reactive sites. Okay? So our standard aldols are direct additions, but there's only one addition that's possible. So we just call it an addition. That makes sense? Okay. So within that section, there's a bunch of different kind of named reactions. You'll hear crossed aldol. You'll hear all sorts of other terms get floated out at you. They're all going back to the same basic structure of this reaction, okay, of this mechanism. You just have to evaluate why each of those things now change the overall reaction.
So why is it, compared to other reactions that we've done that are, we have a stupidly strong as direct addition?
Yep.
Why when you have that negative carbon with that structure, is that not stupidly strong?
Do we have the negative carbon?
You drew it.
What's the important consideration? We have a resonance structure. Do we have a formal negative charged carbon?
Those other ones we don't have resonance.
No. In those other cases where we had stupid nucleophiles, they weren't, they didn't have resonance to stabilize that negative. In this case, we actually have that resonance stabilization. The one kind of trick one, the Gilman reagent. The Gilman reagent, copper versus magnesium, right? That difference in electronegativity causes it to be a 1,4.
So because it has resonance, it's not as...
It's not stupid strong, it's just strong. Yeah. You got to come up with some way to differentiate. Might as well use something stupid. A couple people laugh, that's good enough. So, chapter 19. In chapter 19, it's more synthesis. Okay, so the same general ideas apply as chapter 13. We're looking at synthesis reactions. How do we put pieces together? One of the new things that they kind of address is this kind of term. How could I get these two species to react with each other, to make a longer carbon structure? Well, if we look at the reactivity, both of those have electrophilic carbons. There's no way I could connect those carbons with each other. Right? So what do we want to do if I want those two to react? Could I change one of those to become negative? Absolutely. I could change one of those to become negative by using material from chapter 17, which is on the next exam. I could react the halogen with magnesium. What does that do? When it inserts the magnesium into it, that carbon now becomes very highly negative. I now have a nucleophile that could attack that electrophile. Okay. So by looking for how we can change the charge, that's going to how we help us come up with reagents that would allow us to complete a synthesis. So we could look at a structure and say, how do these pieces potentially fit? How can I get those charges to match appropriately? So remember, identifying charge is huge. The main reason this slide is actually on there is for this special word. We took that carbon that was positive and we made it negative. Okay? This is known as umpelung. That's why I put it on there, just because I think it's funny. It's apparently German for meaning a polarity reversal. You're taking a carbon that was positive and you're making it negative. Way to focus. Okay, so our Grignard reagents do this. Our Wittig reagents do this. If it helps you to remember Willy Wonka, that's fine. I don't really care. It's not that big of a deal as far as a word goes. Okay, it's just it's making carbons negative. Okay. So let's just move beyond that. Okay, reactions that form carbon-carbon bonds are the big ones. We've talked about these, your cyanide, your Wittig, your enolates, okay, which will become really important in parts of chapter 18. They don't have Grignards listed on here because I think that's on the next part of the table. Okay. So there's a variety of ways we can make carbon-carbon bonds. Nearly all of them are named reactions. Okay. The next kind of topic they bring up is this idea of selective reactions. When we talk about a lot of our reactions, or so far, we've really just said, well, it does this. Okay? Where do oxygens attack? Well, they attack the carbonyl carbon as a nucleophile, and we get an acetal. Where else could oxygens have attacked? They could have reacted with hydrogens at the alpha position, in which case we're changing the reactivity of our oxygen. Which pathway is correct? Depends on what you're trying to do. If you're trying to make an acetal, I want it to act as a nucleophile. If I'm trying to make a nucleophilic carbon, I want it to act as a base. Okay? Can we make it do one versus the other? Barely. Okay? That's one of the reasons why when we look at yields in a lot of these reactions, we don't get very good yields, because our control over what the oxygen does is kind of just whatever it encounters first. By limiting its ability to encounter things, we can change that reactivity slightly. Okay? But we're always going to take a hit in our yield because we have those multiple pathways. Okay? So what we would like to do is pick reagents or conditions that would prevent one pathway versus another. So if we went through and take a look at these two options, sodium chloride is now a selective reagent for substitution. Okay? Why would it not do an elimination? What's that?
The conjugate, base or something?
For chloride to do an elimination in that top reaction, I would need to remove a hydrogen so that I could get the elimination. What's the problem with that? What would I be producing? HCl. HCl is a strong acid, which is not a favored species to form, so chloride can't do the elimination. Okay? So these reagents are selective. Not all of our reagents are selective. Okay? And that's where we have to kind of watch out. Same kind of thing happens with our elimination down below. What species are we looking at there? The NaOCCH33. Bulky is a good way to explain that. That would be sodium. Tri isn't a bad idea, but not quite. T-butoxide or tert butoxide. This is sodium tert butoxide, which is a very bulky negative charge. Because it is bulky, can it act as a nucleophile? No, it can only act as a base, which then means the only chemistry available to that species is for it to go through and do elimination in this reaction. Kind of makes sense? So we've talked about reagents, and we haven't directly addressed their specificity. Okay? But that's partly now what has to come in, is we have to be very careful about the reagents we choose when we go through and deal with specific things. Okay? This one becomes more relevant. Why is this one important? What are we talking about forming? We've seen it before. We've seen all of these before. We saw this one very recently. Okay, so more recently than we saw the other ones. And yes, it's making a carbon nucleophile. Where is it making the carbon nucleophile? In the case of the top one, where's the nucleophile forming? The left side. In case of the bottom one, where are we forming the nucleophile? On the right side. What is the difference between the red side and the blue side? Substitution, which is getting at which concept? Heavily tested on the exam. What topic are we getting at when we're talking about the red product versus the blue product? Thermodynamic versus kinetic. The red one ends up being the, sorry, I didn't color code this well. The kinetic one, I didn't color code it well. The blue one is our thermodynamic. It's looking at where the enolate forms. Okay? Why does the red one favor the kinetic? It is a stupidly strong base. That stupid strong base is trying to neutralize its charge as fast as humanly possible. So it's going to react with the most accessible hydrogens. Okay? What happens in the case of the blue one? Okay? And I think I heard somebody maybe say something about sterics.
It's going to be reversible reaction.
Okay, we'll get to that term in a second too. Sometimes you'll hear reference, people say, well, the top one is sterically hindered, and that's why it attacks on the outside. Well, what about the bottom one? That's also sterically hindered. So the steric hindrance argument is invalid in this case. We can't use that. Okay? It is still going to be a base, but now what we've got to do is think about reversibility. It will still absolutely deprotonate at the red position. However, that is now a reversible acid-base reaction. Because it is reversible, we wait longer effectively for the reaction to find the more stable enolate. The more stable enolate is going to be generated at the blue position because it's more substituted. Because it is now more substituted, that stabilizes. We get that enolate for a long enough period of time where that nucleophile can go through and react with the carbon in the next step, placing the electrophile or the methyl at a different position.
Would hydroxide be like a better one to use since it normally wants to make a more substituted? No?
It's not really going to matter.
Really?
Okay, yeah, the difference in basicity, it's really the strength of the base.
Okay.
That's what's dictating this. The issue with hydroxide is that hydroxide is a better nucleophile. So we could start to see an increase in the acetal side products. I don't want an acetal here. I actually want to do the reaction. Lithium aluminum hydride is just going to attack the only electrophilic site. Where's the only electrophilic site? The carbonyl carbon. Okay. So that's now a separate point. There's only one place to react.
What if you put a protecting group before you...
If we put a protecting group on here, what are we protecting? The carbonyl. What would our reactivity then be at that point? Where's the other reactive site in our starting material? There isn't one. So I could put a protecting group on it. Great. You've now protected that carbonyl. We also don't have any other sites that are reactive. So what would you do with the structure?
Why can't you just take out a random hydrogen?
You can't ever just remove hydrogens from a structure. The only reason you can remove a hydrogen is because you form a stable conjugate base. If your conjugate base is not stable, you can't do it. If we put a protecting group on there, there's no more carbonyl. no more carbonyl, there's no more acidic hydrogens because we don't have the enolate stabilization. Okay? So the base we're choosing ends up being selective. We could refer to those as thermodynamically favored or kinetically favored. We could also refer to them as reversible or irreversible. LDA, the top one, would typically be referenced as a or an stupidly strong, which would mean it is irreversible. So it forms only the kinetic. The bottom one being strong is now a reversible base. I would favor the thermodynamic. Okay? So we have some selectivity and we've seen that pop up. Okay, where it becomes more important is we move to our reduction and oxidation. When we look at our reduction reagent summary, we've seen a bunch so far. We're talking about nonpolar pi bonds. We've got hydrogen with some metal, platinum, palladium, or nickel. Okay? Those are super, super common, but they are insanely not selective. Okay? That means if there's any pi bond, hydrogen gets added to it. And not only that, it adds all the way down. So if I had an alkyne instead of an alkene, it's fully reduced. Okay? What happens with the new section? Well, not quite the new section. There's our triple bonds. We bring in our triple bonds, we now have some selectivity. We can take hydrogen and a poisoned metal. That poisoned metal is typically platinum or palladium. Okay? But if it was just platinum or palladium, it would be the same reaction, so we have to poison it. What do we poison it with? Okay, sometimes you'll see BaSO4. I think calcium carbonate. If it is calcium carbonate, that is typically now referenced as Lindlar's catalyst. That is one you should check and verify on, but I'm pretty sure that's the case. Okay. They're all poison catalysts, but what makes it specific to Lindlar is what you're poisoning it with. Okay. So they're all doing the same thing. We aren't going all the way. Okay. Within that, we're now selective. We're selective because we form an alkyne. We're also selective because what do we make? A cis alkene. Okay, so we have some stereochemistry associated with that. If we switch this up and now go sodium metal and ammonia, well, that'll react with alkynes as well, but this time it'll produce a trans alkene. So we have to remember those bits and pieces and tie that information to them. The how and why these work go back to mechanisms. The mechanisms for the raw platinum, palladium, or nickel catalysts are not well elucidated. They certainly are not well enough for us to be able to discuss in the class. Okay? We've got the kind of general idea of it just fitting down to a surface and then hydrogens being added on the same side. With the case of the sodium metal and the ammonia, that mechanism we have talked about. If you want to look at that mechanism, we can do it, but after class. Preeti?
Why does, if you add the, if you go on the very bottom left, right?
Yeah.
Why do you form an alkene instead of an alkene?
That's because of the poisoning of this. So how is that poisoning affecting it? Something about those structures prevents an alkene from binding to the substrate. If the alkene never makes it to the metal catalyst, the catalyst can't function, and all you have is hydrogen floating around with an alkene. Hydrogen can't react with the alkene in and of itself because hydrogen's too small. Okay? It can't straddle those two carbons. So you need the metal surface to do that. Which I fully admit is a completely wishy-washy answer. But that's the best we got. Best I've got, I guess. Okay. The next thing that pops up is we could also go through and now look at these pi bonds. What is special about these pi bonds? These are now polar pi bonds. In the case of polar pi bonds, they aren't going to react with our poison catalysts or our sodium and our ammonia because those reagents reacted with alkynes. Would our carbonyls react with hydrogen metal? sorry, hydrogen is not a metal, hydrogen gas and a metal, platinum, palladium, or nickel? Yes. They will go through and force a reduction with those. Those platinum catalysts are exceptionally not selective, and they will add hydrogen across the pi bond. All right, so let's take a look at that first one. If I was to go through and react that first structure with hydrogen gas and platinum, I need to add hydrogen across the pi bond. What functional group would I end with? I add a hydrogen to one part and I add a hydrogen to the other part. The functional group I end with is an alcohol. I don't go all the way down to the alkane. Why not to an alkane? In the case of the nonpolar pi bond, they were both carbons. In the case of the carbonyl, they aren't both carbons, so I can't completely get rid of the oxygen. The reactive site is at the oxygen and the carbon. We're adding hydrogen across that. That's how we get the alcohol. Same basic mechanism as you get, or basic reaction as with the nonpolar pi bond.
Are we still using the poison metal down here?
No,
Okay.
we're not doing the poison metal.
Just platinum?
Just platinum. Yep.
Okay. Because you can. Is that what you said?
Yeah, we can't.
Can?
Can't.
Cannot.
Cannot.
Okay.
Right. Needs to be a standard metal.
So, when we were studying this before, right, we had nucleophile and
So we have to be careful in reference to our nucleophiles and electrophiles attacking. With hydrogen, that is not a nucleophile or an electrophile. Okay? So when we're looking at hydrogen getting added, we have no nucleophile or electrophile. It's a complex reaction mediated by the metal catalyst transferring electrons around. Okay? Probably through some kind of radical type situation. So there is no nucleophile or electrophile. Okay? Which could also explain why we don't lose the oxygen. If we go through and look at the two remaining reagents that are shown, what is special about those reducing agents? Okay, if we look at the zinc mercury one, we start with a carbonyl, right? What do we end with? An alkane. What happened to the oxygen? It's gone. It is completely removed from the structure. So these new reducing agents will reduce the structure so far that we entirely lose the oxygen. That's a really big step up as far as our reduction abilities. Okay? All three of these new reagents will go through and do so. How do they go through and do so? Well, we would have to evaluate that by looking at each of the reagents. What do you see potentially happening in the reagent for that first reaction? So what do you see in that box? The red box in the lower left. Two nitrogens. What do nitrogens have? Lone pair electrons. What can those electrons do? They could form a bond by acting as nucleophiles. What does my carbonyl act like? An electrophile. And this gets right back to what you were suggesting, Pretty. This now matches the mechanisms that we've been looking at. Why did we not talk about these reducing agents earlier in the semester? We needed the nucleophilic addition. We hadn't talked about nucleophilic additions yet. All of these are moving through some type of nucleophilic addition reaction. Some of them are more complex than others. The first one is a relatively straightforward one that we actually already discussed. That one's known as the Wolff-Kitchener, which I think I'm spelling right. Okay. A Wolff-Kitchener reaction. I'm going to bet they're German. Okay. Almost all of our discoveries came from Germany when it comes to OChem. Okay. So that is our Wolff-Kitchener reduction. Allegedly works really well. My experience, it worked awfully. Okay. Next one. What do you see in that one? Okay. A Clemenson. How many of you look at that one and are like, I totally understand the obviousness of that mechanism?
Is it because of the zinc and the mercury?
The zinc and the mercury help to catalyze the removal of our oxygen. It is kind of a neat reaction. Okay? I would argue that because you're dealing with so much metals and craziness, that's why it gets named. Okay? Last one at the bottom. What do we see inside that first step? Thiols. What is special about a thiol? Yep, I like the enthusiasm there. We have electrons, meaning the sulfur can act as
Nucleophile?
a nucleophile. It's matching our nucleophilic addition and elimination reaction. Okay. Those mechanisms, to my memory, were covered in that redox video. So unless you have specific questions about those, we aren't going to go into those mechanisms. Ultimately, what you need to know is those reagents, and most importantly, the conditions tied to them. So we're at a couple questions.
Do they all work on aldehydes as well?
Yes. So these are all aldehydes and ketones. Preeti?
Yeah, so where's the nucleophile on
The Clemenson one, I don't remember off the top of my head. That's one that I have to look up the mechanism on. It might come from the water, and it might be the zinc. I don't remember exactly. I remember drawing it out and being like, wow, that's kind of a bizarre mechanism. And then I completely forgot about it.
So do we need to know if it's under like basic, acidic?
So, looking at these and deciding why I might, evaluate one versus another. Okay? Because this gets to that selectivity aspect. These are now selective for our carbonyls, which is a good thing. Okay? But what if there's other things in the structure that I need to be concerned about? So one option is looking at the other reagents used. In the case of the Wolff-Kitchener, what reagent am I using? Hydroxide, which is a strong base and nucleophile, which means in the rest of my structure, what do I expect to not have? Something that is acid-base reactive, because that's going to potentially neutralize the Wolff-Kitchener reaction and prevent it from functioning. When we move to the Clemenson, we're looking at the presence of a strong acid. So what do we expect to not find in our structure? Something that's remotely basic. If that species shows up, we're going to neutralize the Clemenson reagents, preventing them from functioning. Okay, the last one, okay, with our sulfurs, what did the not with the sulfurs. We had an acid catalyst, again, to help initiate this. Okay? So I want to be thinking about those other reagents and how they could affect the reaction. Okay? We go through and look at these again. Stop erasing all those things above, because I don't want those to be thought about. We had our nitrogen clearly acting as our nucleophile. How about the sulfur? Clearly a nucleophile. Okay? In the Clemenson, I'm pretty sure it's actually not water. I think it does something really weird with the metals. Okay? We don't have a strong nucleophile. So what if there was other electrophilic sites in our structure? What would electrophiles potentially react with? Nucleophiles. Is the Wolff-Kitchener a good one to mix with? No, because what could the Wolff-Kitchener potentially do? React to those other electrophilic sites. So when we're looking at these reagents, we have to be careful to decide what's going to be targeted and make sure there isn't something else present. Okay, this is where synthesis can become very tricky, because we now have 3 reagents doing the same thing, but the conditions change. Kind of make sense? Okay. So, propylbenzene. Target contains 9 carbons. We're going to have to use some kind of carbon-carbon bond formation, because the rule is 8 or fewer carbons. How could we go through and synthesize this? What bond do you think we would make? How about anything in the ring? No. Okay, that's probably a good idea. Let's leave the ring alone, which means I could be trying to make this bond. Or I could be trying to make
From the ends of that guy?
Okay? We could be looking at how to make any one of those. There was a suggestion made for MGBR. Okay, so you want a carbon nucleophile as the magnesium structure, right? Coming from where? How many carbons do you want with that Grignard?
We can put a phenol.
Is it going to matter? How many carbons are in our product?
Up to the phenol. Like,
Okay.
I want a positive benzene.
So you're suggesting that we want to make that bond,
Maybe.
where this is our Grignard. Yeah? What does the Grignard attack? An electrophile. Which type of electrophile?
Carbonyl carbon.
Carbonyl carbon. Am I allowed to form an aldehyde there?
Yeah.
Sure. Okay, so we could go through. I'm not saying you're wrong. You don't have to be too defensive. That's okay. So we could go through, have our Grignard, right? Where the Grignard could potentially go through and attack. What would we end up with? We're going to work right to left now. What would our product be of that? Carbon chain is added. We broke one of the pi bonds. And we have CH2, CH3. We've got our benzene. We've got the propyl. We still have that hydrogen. Do you know how to get rid of that? Okay, we could do an elimination. How do we eliminate that? Okay, we could add a strong base. Usually a good option for an elimination reaction, because what are you suggesting needs to happen? The base comes in, kicks out our leaving group, yeah? That would then make an alkene. We'd have a pi bond. Does anybody want to flag that as potentially problematic?
Just have the OH as a leaving group, but it's going into
We have the OH as a leaving group, which we said is questionable. It's okay if it's leaving into a system that's similar to it. Okay. Is that hydrogen acidic? Can I form a negative carbon? No. When was it allowed to be acidic? What was it next to? Why was that allowed? Why is that hydrogen now acidic? Because we have resonance to stabilize it. Do we have that resonance to stabilize it? No. So is that hydrogen acidic? No. So I like the idea. I do want to run an elimination, but adding a base isn't going to help me do that elimination.
PBR3.
Okay. So one option is to say, well, the OH is the problem, so I'm going to go through, stupid stuff underneath this, is get rid of the OH and replace it with, there's a variety of options for that. OTS would also work. The first option I heard was a bromine. How do I get the OH to be substituted for a bromine? PBR3. Chapter 10. Now that I have a bromine, I don't have to worry about the base reacting with that secondary group, and I could now add my strong base, like hydroxide. Problem with hydroxide. What can be both? Hydroxide could be a nucleophile and a base. If it acts as a nucleophile, do we have a substrate that's nucleophilically susceptible? Yeah, I don't want hydroxide. I want something that is specifically a base. What could I use as my base? A nucleophile that would just take us right backwards. We don't want it to do that. So we want something that is a strong negative that is non-nucleophilic, like T-butoxide. Okay. T-butoxide would now get us to this elimination product. Fantastic. Now what can we do? Because remember, we wanted propylbenzene, no pi bond. How do I get rid of it? H2 and platinum. Cool. You ran a Grignard reaction followed by a substitution, followed by an elimination, followed by a reduction. Okay? Is that what you had to do? No. Because of the way Mike asked the question. Fair enough. You didn't have to do it that way. What else could you have done?
Is there an easier one?
Easy is all relative. I used to bike 16 miles to work because I thought it was easier than buying a car. Right? I still think it's easier than buying a car. I still hated buying a car. Right? So easy is definitely relative because none of you thought that that was an easy process. I would bet. Could be wrong. So what else could we have done? I'm going to say we want to make that bond. Except in this case, I'm going to say that the CH3 is my electrophile. It's positive. Which then means what? That carbon had to be negative. How do I get a negative carbon?
Oh, I see.
Okay, we could go back to the Grignard. I don't necessarily have anything against the Grignard, but I want to say no to the Grignard because we already did it.
Okay, strong base.
Strong base with what? Okay, I want that carbon to be negative. A strong base isn't just going to remove a hydrogen from an alkane. Okay, so say that again.
You had an OH on that, or you should use PPH3.
So you're trying to do a Wittig reaction.
You started with an OH.
Yeah, we can work with that. That's definitely not what I wanted to do, but you know. Wittig does work. The Wittig is harder for me to process backwards though on. So we want, whoops, carbonyl. So instead of this being, we're going to have that be negative. So this is our PPH3 with our negative. The negative can come in and attack. Bust that open. Where would that take us? To the alkene. Now what do we do? Now you could reduce it, our H2 and our platinum, to get our propyl. People kind of see that one?
But how did you get the carbonyl carbon on there?
So remember, what are we trying to do?
Trying to produce.
We're trying to figure out reactants to make propylbenzene. So because he was saying we want to do a Wittig, we just said, okay, I'm going to put a carbonyl carbon there. Okay. Would that fit within the rules? What were the rules? 8 or fewer carbons. How many carbons in that? 8, which means fits within the rules. The methyl will now go through an attack. We'll go through, do our Wittig reaction, and we could go through and run that reaction outwards. Okay, so going through a Wittig, we could generate that. Okay, which is not what I wanted. I was fishing for something else. I still want this to be bromine. How can I get that carbon to be negative so that it goes through and attacks that? LDA is not a strong enough base to make a negative carbon. It is stupidly strong. It's still not stupidly strong enough. The pKa of the alkane is somewhere on the order of 50. Okay? Your stupidly strong LDA is still 10 to the power of 20 times less strong. What if I had a carbonyl here? Would that position now potentially be acidic that I could remove a hydrogen? Yes. Okay. So if I initiated that, this is coming back to that structure. That could go through and attack the Grignard. or not our Grignard, the carbonyl. We'd have our 3 carbons. How do I get rid of the carbonyl? I could use my Wolff-Kitchener. I could use the Clemenson. Okay. Can I use H2 and platinum? No, I'd end with the carbonyl, and I don't want the the alcohol, and I wanted to completely remove it. Okay. So depending on where you look at your structure and where you decide to slice the compound to break it apart into those pieces, you can end up with a variety of different pathways. Which of those pathways is best? Or which of those pathways is the answer?
Depends on the conditions you're looking at.
Depends on the conditions you are told to use at the beginning. Okay? We've still matched all of the conditions we were told to use, 8 or fewer carbons. Which of these pathways is the best? We've covered 3 of them.
All of them are the same.
We can make the argument that all of them are the same. Depending on who grades, I grade yes.
You want the least produced.
What other things should we be concerned about?
How many steps?
How many steps? If it takes 50 steps to do a reaction, but I've got synthesis in 3, who's better? The 3. Why is the 3 better? It's faster. And everyone goes, well, but 50 still worked. Okay, we go into lab, and every time we're in lab, you have to do a 50-step reaction versus a 3-step reaction.
And there's chances of missing.
You're not going to be happy about that. So the more time you spend in lab, the more likely you make a mistake. We want shorter pathways. Right? What I want to see is that you know how to make those connections. That's what you get graded on, not necessarily the shortest pathway. Kind of makes sense? Okay. So, alcohols. We just looked at reduction, so now we also have oxidation. We just reverse it. There are only 2 reagents that you need to know as far as oxidation reactions go, right? Or for alcohols. Chromic acid and PCC, pyridinium chlorochromate. The way I like to reference them, for those of you that were in the lab, it's already repetitive now. PCC is politically correct chromic acid. I like politically correct humor. It's just not quite as funny. Okay? Same thing with PCC. Right? It still does the same thing as chromic acid, but it just doesn't do it quite as well. Okay? There's only one place where you can differentiate between those 2. That one place is with primary alcohols. If we initiate a primary alcohol oxidation, the very first step results in a carbonyl. What functional group? It ends in an aldehyde. If I oxidize the aldehyde again, I end up with the carboxylic acid. So PCC will do a single oxidation. It will convert an alcohol across to the carbonyl, and there it stops. Okay. Chromic acid will do the exact same thing, but it will continue to oxidize if there's an option. That option has to do with the presence of more hydrogens that are removable. In the case of the aldehyde, there's still a potential possibility to remove that hydrogen. That's why we can continue to oxidize. Okay, is there a question? No? Okay. So you are responsible for knowing those 2. One of the things that's challenging with chromic acid is there's a whole bunch of different ways it can get written out. Pretty much if you see chromium and acid, it's chromic acid. Okay? And within that, if you see chromium, and not so much the acid, but the aqueous part. Okay? Chromium with water is chromic acid. Chromium without water is PCC. Okay? PCC is that pyridinium. That's what differentiates it. Instead of water as a solvent, we have pyridine. And that's why we get the 2 different oxidation reactions, is literally just the presence of water. Okay? Where does that happen? Okay? In our mechanism for oxidation, we've got our chromium structure, or our chromate structure, similar to our permanganates and all of that. We have a very electrophilic site on the inside, okay, that metal center. Oxygen is a stronger nucleophile than our alkenes. can immediately attack inwards. That attack with a transfer of some hydrogens.
We saw that same exact one on the exam. I remember.
Yep, I know.
No.
The last exam, when we had it with alkenes. We would form the chromate ester. Okay, why is this known as a chromate ester? What does an ester look like? What is the ester functional group? It's a carboxylic acid without the H. Why is this called a chromate ester? Well, there's the oxygen, carbon, chromium, and carbonyls. It's a chromate ester because that is chromium and not carbon. Otherwise, it's an ester functional group. Right? The chromate ester is what goes through and does the oxidation reaction. How? Something slightly basic in solution goes through, removes the hydrogen, the electrons shift, and the electrons go out to the chromium. Okay? Is that a strong base?
No,
No. How do you know that?
it's not charged.
It's not charged. How else do you know it's not a strong base?
It is not hydrogen.
Not necessarily. Has to do with the reagents. Both of our chromium solutions, both the PCC and chromic acid, are acidic environments. Okay? Chromium is missing enough electrons here. It wants to transition to the chromium 4. So it will help polarize that bond enough that oxygen will steal electrons from that hydrogen. That makes that hydrogen acidic, and that's why the base can come in and remove it. That base is something remotely basic in solution. That could be more alcohol floating around. That could be water in the case of the chromic acid. It could also be pyridine in the case of the pyridinium. That gets us to our aldehyde. Both PCC and chromic acid initiate the same thing. They get to the aldehyde. Right? The mechanism would be identical if we went through and switched it to a secondary alcohol. No changes whatsoever. Right? So why does chromic acid oxidize this further? Is the oxygen in the aldehyde a nucleophile? We've had this conversation at the very beginning of the unit. It is not, which means it can't attack the chromium or another chromium. Okay. So regardless of whether it's chromic acid or PCC, shouldn't it stop here? There's no nucleophilic oxygen to attack chromium. There's a suggestion about hydrogen. What is your suggestion about hydrogen?
Hydrogen attacks chromium?
The hydrogen is not nucleophilic either, so it can't really do anything. Okay. The key difference between these two reactions has everything to do with the solvent. In the case of chromic acid, what's the solvent? Water. In the case of PCC, the solvent is pyridine. Okay. And if we actually make this officially pyridine, we need the lone pairs. Okay, so now the question, well, why? Why does the water make such a big difference? What can water do? Give electrons. You mean it's a nucleophile? Yeah. Is an aldehyde an electrophile?
Yeah.
We literally just spent 4 weeks talking about aldehydes as an electrophile. Yes, it is electrophilic. That carbonyl carbon is an electrophile. What happens if water attacks that spot? What do we get?
Oh, wait.
We would get a couple things. One good first answer was a hemiacetal. What is special about the hemiacetal?
Not stable.
It is unstable.
So it's going to react again.
What do you mean it's going to react again? So we could end up after 2 acid-base reactions with our final hemiacetal. What have we now formed? Diols, and ultimately an alcohol. What reacted with chromic acid? An alcohol. In the presence of water, water will react with the aldehyde to form the acetal. The acetal is now an alcohol, which can be oxidized by chromium. PCC does not have water in it. Its solvent is pyridine. Pyridine is a horrible nucleophile. Why? It is too sterically hindered. So the pyridine can't attack the aldehyde, in which case I'm only left with the aldehyde in solution. Is there an alcohol?
No.
Nope, which means
Doesn't have.
nothing happens. PCC stops at the aldehyde because that's it. It's all it can do. Chromic acid will continue to oxidize only because water is present. This has actually been tested. If we take PCC, pyridinium chlorochromate, and I just add some water to it, guess what happens? It continues to oxidize. It ends up at the carboxylic acid. Water's the piece that's actually causing the secondary reaction. Okay? Which I find insanely cool. Okay? We're taking that acetal chemistry from chapter 18 and we're applying it into other reactions. Okay?
Still got to be cognizant about the characterization of the alcohol, right?
What do you mean the characterization of it?
Primary, secondary.
Primary, secondary, tertiary, yes. Okay. Why does the ketone, or sorry, the secondary alcohol not continue to oxidize?
Because it can't go any further. There's no hydrogen present afterwards.
If we were with the ketone, what happens? We would still end up with the diol, but do we have any hydrogens that we could quickly and easily remove? No, we have carbons. So with a secondary alcohol, I form the ketone. I will form hemiacetal or hydrate. Doesn't matter. Okay? There's nothing that chromic acid can oxidize or do to oxidize that further. Okay? So after a quick workup, I end up right back with the ketone, and that's the end of the secondary alcohol. Okay? So in our oxidation summary, this has it all set up there. So chromic acid on top, PCC on the bottom. Looks kind of crazy, it really isn't that bad. The top one, we have 3 R groups, right? In the top case, one of those is a carbon, which means I'm looking at a one of them is a carbon. I have a primary alcohol. In the case of a primary alcohol, what do I end up with? A carboxylic acid. And the next one down, how many carbons do I have? 2, which means secondary. In the case of the secondary with chromic acid, I end with a ketone. 3 carbons. Tertiary, I get no reaction. Right? 2 things are written here. You could see it written as no reaction. You could also see it as the alcohol just getting rewritten. Okay? Because that tends to trip people up. They go, oh, well, no reactions there. It must have oxidized then. Okay? Don't get tripped up by that. If you think it's no reaction, look for the starting material. Okay? With PCC, we're starting the reverse direction, primary, secondary, tertiary. The primary gets you the aldehyde, secondary, ketone. Kind of, sort of? Okay. Protecting groups. Okay? Protecting groups I've ultimately saved to the very, very end because they're kind of a questionable thing to discuss. Okay? The primary reason behind why they're questionable to discuss. The whole point is if I go through and look at this reaction, I'm trying to go from this A structure to the B structure. And they say, well, I can't do that reaction because this other group will react with my reagents. Okay? In this case, they're calling it labile. Labile just means that it can come on and off. Okay? So it's a group that could react under those conditions and they're transferring from A to B. Okay? Which means if I try to run that reaction, it doesn't work the way I want it to. So instead, what I go through and do is I do a protection step. That protection step changes the labile group into something else. That something else is no longer reactive. Once it is no longer reactive, I can do whatever I want to A to convert it to B. Now I can undo the protection and take me back. Okay? So to complete one step, how many steps do I have to do? 3. Okay? And in this case, it's literally 2 steps forward and 1 step back. Okay? If you're trying to get somewhere, is that how you walk? No, why not? It takes forever. Okay? You are now in lab for 3 reactions as opposed to 1 reaction. That is tedious and time consuming. We don't want to do that because of the time commitment. So protecting groups are generally frowned upon because it takes more time, which means somebody has to pay you, somebody has to take care of your waste, somebody has to take care of all the chemicals. Okay? So protecting groups, just from the sheer kind of economic standpoint, are a bad idea. Okay? More recently, we've become slightly more concerned about the environment. What do you do with all the chemicals once you've made them? They go somewhere. You just put them in a bottle and hope somebody takes care of it. And we pretty much do the same thing. We take the bottle and put it in a bigger bottle and then pay somebody to go take care of it. Theoretically, they take care of it in a nice fashion, but who knows? Okay? That's why we have the government to look into that. Okay? Theoretically. Okay? Probably just getting dumped in the ocean because we're good people that way. If you go through and do this, the chemicals from your protection step, are they necessary to get to your product? Are they in your product? No. So all the chemicals you use in that first step are now waste. How about the second, or the deep protection? Also waste. Which means all of those chemicals that didn't take you any closer to your goal now get thrown out where somebody has to take care of them. Burned, right, which produces CO2 and creates environmental issues. Thrown into the ocean, it kills all the fish, right, or poisons the fish that we then eat, and then we get poisoned. Right? So there's a big kind of environmental aspect behind it. That field is known as environmental chemistry, is more the study of it.
Environmental science?
Green chemistry. Yeah, people talk about green chemistry all the time. This is one of the things they talk about. Okay, there are certain tenets behind green chemistry. Ultimately, what they're focused on is minimizing chemical usage. Okay? Green chemistry is not about not using chemicals. We have to use chemicals. It's about using them intelligently. So how could we change to prevent using a protecting group if this is what I have and this is what I have to do?
Take it out.
Figure out what to do with the waste in the end product.
Change my whole reaction. Okay? Ultimately, what I started with was probably something that didn't have the labile group or A. Change how I designed my synthesis to make sure the labile group and A are never in the structure at the same time until the very end. Okay? So you have to change how the synthesis is done. That requires a whole lot more thought. Okay? But that forethought could potentially limit costs, and it could also limit toxic exposure to chemicals. Okay? When organic chemistry was originally kind of developed, people washed their hands with benzene. Anybody know anything about benzene?
They also used it to decontaminate.
Yeah, we'll talk about, well, we won't talk about that, but that's also true. Why would you, what's the problem with benzene? It's actually a pretty heavy-duty carcinogen, and people were literally pouring gallons of it over their hands into the sink. Okay, why? It does a really great job of dissolving organic compounds. That's phenomenal. So my hands are now all sparkly clean. Okay, I might be missing a few layers of skin, and I may now have cancer, but at least my hands are clean. Okay? In the safety video, they're like, don't ever use your mouth to pipette liquids, use the bulb. Okay? Why do we use the bulb and not your mouth? So you don't suck chemicals into your body because that's stupid. Why do they even have that in the video? Because that's the standard protocol 50 years ago. Okay? Yeah. Okay, they did a lot of really stupid stuff without thinking about how it affects everything else. And it's not necessarily because they're stupid. It's because we just didn't think about it. Okay? We now think about things a little bit better, theoretically, Okay? So because of that, we start to see the fade out of protecting groups. Okay? It is an important area of chemistry because it does shield and protect things, so it is something that we should at least talk about. But as an area of chemistry, it's starting to disappear because we don't want to do it. Does that make sense? Okay. So, one of the options, if we go through and try and initiate this reaction, we've got this A, well, there it is. There's that A group on the side. Okay, which Marcus, you'd have to look over here, unfortunately.
I can see it on the.
You can see it? Okay, good. There's that A group that could potentially react. So what I want to do is make sure that the carbonyl can't react. So what do I do? I want to put on ethylene glycol. Ethylene glycol will form that structure, which is an acetal. Okay? With the acetal in place, I no longer have an electrophilic carbon. I can now do chemistry at position A, and I can change A to B. And then I have to remove the acetal. I remove the acetal by adding water and an acid, and it takes me back to the carbonyl. Okay? So the acetal chemistry that we talked about that was kind of loosely like, why are we even doing these if they're not very thermodynamically favorable, is we can use them as protecting groups. Okay? There are other, I don't even want to see that. There are other groups or protection type reactions that we could run. And your textbook lists out a whole bunch of them. And while that is all neat and fine and dandy, you could go through and look at them. The odds of you ever really encountering many of them is pretty limited. Okay? I will say that we oftentimes will refer to, do we have actually any up there that I can quickly reference? No, I don't. Okay? We will sometimes refer to them by the name of the reaction that made them or the name of the reagent. So for instance, the first two, what functional group are we making? What are we ending with? Ethers. How do we make ethers? There was a named reaction that is also on the slide. A Williamson ether synthesis. Why do ethers limit the reactivity of the alcohol? What did they change? They got rid of the hydrogen. We no longer have an acidic hydrogen or a protic hydrogen by making it an ether. Okay? Once I've made the ether, what do I then also have to be able to do? I have to be able to take it off. So in all of these protecting reagents, there's a process to put the thing on. There's also a process to take the thing off. You would have to know both pieces. Some of them are more straightforward than others. Okay? DHP. We put it on. It's just forming another ether. Another ether. Okay? That one is just a complicated version of, what was this other one? Whatever the name of that one is. Okay? The methoxymethyl ether. Okay? It's the same thing. Okay? Why do we call it DHP? Does anybody want to figure out how to name that compound? There you go. That's why we call it DHP. How do you undo DHP? The same way we undid the Williamson ether, because it's just an ether. When we move to the TBDMS, tert-butyl dimethyl chloride. Okay? This is pretty much the same thing as our tosylate, except instead of it being sulfur, it's silicon. Why? We get a slightly stronger bond. Okay? Because it's a stronger bond, what does that mean about the protecting group? It's stronger. It's a little bit more sturdy, harder to remove. How do we remove it? A very specific reagent. Not only a very specific reagent, what's the counterion? Fluorine. Okay? That fluoride is what's helping to initiate or remove the protecting group. So we have very specific reagents to force it off. That one might be a better synthesis for an alcohol or protecting group than for the top one, because in the top one, what's my reagent? H3O+. How often do we see H3O+? All the time. How often have you seen tert-butyl amide? Never.
Today.
Today, okay? That reagent is so specific that the odds that we would ever encounter it randomly in our synthesis, very unlikely, okay? So we could probably keep that protecting group on there for a significant amount of time. Kind of make sense? Okay. So, aldol practice. Okay. I know the aldol was at the way beginning of the lecture, but here's a bunch of aldol reactions. Let's take a look at the first two. And we'll erase all of these. So what happens in the first step for the very first one? That's a lie. Because of time, we're going to do the second one first. OET, how is that reactive? It's a base and a nucleophile. Where's there an acidic hydrogen? Wait, what? Can you say that again? There's literally no acidic hydrogens in that structure. Okay? This is super common for students to try and remove the aldehyde hydrogen. Okay? The easiest answer, which apparently has been said in other classes, the aldehyde hydrogen is not acidic. It just isn't. The longer answer is remove the hydrogen, look at the conjugate base. It's not stable. Okay? So you cannot remove that hydrogen, which means OET cannot act as a base. So then it could act as a nucleophile. Where's the electrophilic site? The carbonyl carbon. What would we end up forming? O minus and then an OET, which is a hemiacetal. Okay? We could continue to push that all the way to the acetal. Are those stable? No. What's the product? I'll be extra tricky for you, but I'll write it up. Your product is benzaldehyde. And it'll be your job to go through and look it up, figure out what that is. It doesn't matter. Take a look at the first structure. Is there an acidic hydrogen? I just drew it on there. Yes, there is. It's that red hydrogen. The base can come in, remove the hydrogen. It is acidic because?
Is it the same thing? If benzoate has the same exact chemistry?
Yes.
Yeah.
Okay. It is acidic because resonance. Okay. So the next part on this, I want to go ahead and give you a cheat to get through this, because this case we will be doing an aldol. So this is going to look a little bit weird, but it'll work. Okay. I did a really weird bend on that, but it is still the right number of carbon because I want my nucleophile aimed down. Then what I'm going to do is draw my other structure, because the aldol reacts with itself right underneath it. Right? What does the nucleophile attack? The carbonyl. So it forms a bond. At the same time, it breaks one of the bonds to the oxygen, right? Okay. We could potentially protonate that. That's why I pushed the other arrow. Now what could happen? Why is that it? So that's my aldol, right? This is an aldehyde and an alcohol. I have an aldol. Typically when we talk about aldols, we get aldol condensation. So I would need to do an elimination. To do an elimination, what do I have to remove? A hydrogen and a leaving group. I've got a leaving group. It's crappy, but it's a leaving group. Do I have a hydrogen that is acidic? Where position would it need to be at?
It'd need to be where that blue and purple.
Where the blue and the purple intersect. How many bonds are shown to that position? There is no hydrogen, which means what happens?
That's the answer.
That is the answer. It stops right there at the aldol. To do the aldol condensation, you must have two acidic hydrogens. Okay? So you can look at your starting aldehydes and be like, well, that's not going to do a condensation. It's going to stop at the aldol, just by evaluating your starting structure. Okay? With that, we're done.